Hi everyone, welcome back. Today we're going to be talking about how we use the unit circle. And before we can actually get there, this is actually a giant skill we're going to be developing over the course of the next few days. Before we get there, we are going to be talking about the 6 trigonometric functions. Now, you should have learned about these functions in geometry already, so this is going to be for the most part review. Our objective is that we're going to be able to identify and use all 6 functions given any angle. So, the 6 functions that we talk about are often remembered using this mnemonic device, so, ka, toa. And this mnemonic device works mainly for the first 3 of them, but the second 3 of them are just a manipulation of it. So, the first function we talk about is sine, and this is represented in the word so. Sine is going to be the opposite divided by the hypotenuse. Right, so every right triangle given an angle is going to have an opposite side and a hypotenuse, and that is how we are going to sit there and actually use these. Looking at cosine over here, so for cosine is represented in the word ka. Ka, C stands for cosine, A stands for the adjacent side over the hypotenuse, and then tangent is the last part here, that's the toa. So that would mean that it is the opposite divided by the adjacent. Now, these are like the main 3 trig functions, but across from them you can see 3 additional ones. So CSC, this is cosecant. Cosecant is just the flip of sine. So this would be the hypotenuse divided by the opposite. Secant, which we denote SEC, is just the flip of cosine. So this would be the hypotenuse over the adjacent. And finally, we get cotangent, which is just the flip of tangent. So this is going to be the adjacent over the opposite. Now, it's relatively easy using this mnemonic device, SOHCAHTOA, to remember these 3 over here. Once you remember those 3, then as long as you know that these are all just flips of the original 3, then you just need to remember which one goes with which. Now, there's a lot of ideas that are probably floating around in our head right now, but this is the one I always think to myself. I always get frustrated when I look at the first letter of these and I realize that they're different. And it's actually the same down here when maybe they could have just been the same. So in this situation, what I always think to myself is, I know sine, cosine, tangent are the original 3, but then when I get to cosecant, secant, and cotangent, the cotangent and tangent are easy to put together, but I always think to myself, well, it would have been really nice if they would have just made it so that it was S with S, but instead it's S goes with cosecant, right, or sine and cosine. I just look at the first or sine and cosecant go together, and then for secant and cosine, it's just that the letters flip each time to get to the flip version. So, remember it however you want, but you're going to have to know all 6 of those trig functions and be able to use them at any time. So looking over here, this is basically what we talk about. So we got 2 problems here, so we'll do this kind of twice. But I think we're going to change the second one. So right here, we're being given an angle, and this angle is being called theta. That's how we say, whenever we say a little 0 kind of with a line through it, that's a Greek letter, theta. And in this particular situation, we have the side y, the side x, and we're just going to say this is the side r. Now, depending on the angle that you are given, the side right across from that angle is known as your opposite side. The hypotenuse is always the longest side of the right triangle, and that's always across from your right angle. So this would be our hypotenuse up here. And at the very bottom, that leaves our adjacent side. Now, the adjacent is always the one I find last, because it's maybe sometimes the most confusing one. But remember, a couple things to remember. Your hypotenuse is always across from your right angle, and your opposite side is always across from the angle that we are caring about or considering. So in this particular situation, remember the word SOHCAHTOA, SOHCAHTOA. Sine is the opposite over the hypotenuse. So in this situation, our opposite side was y, and our hypotenuse side was r. So sine of theta is going to be y over r. Now for our second part of this. So for the second part of this problem, our cosine. Well, this theta is still our angle, so we take the side adjacent to that angle, which in this case was x, and it's x divided by our hypotenuse, which is r, right? The cosine is the adjacent divided by the hypotenuse. The adjacent was x, the hypotenuse was r. Tangent is going to be the opposite divided by the adjacent. So this is going to be y over x. Now, again, all you need to do to figure out cosecant, secant, and cotangent is realize that these are flips of their other version. So sine goes with cosecant. That's just the flip, so this is going to be r over y. Cosine goes with secant, so this is going to be r over x. And cotangent goes with tangent, so this is going to be x over y. Now, I'm going to flip all of these just to the same color right now, just so that we can kind of try to do two problems at once here. So, this is my blue problem up here. And then this is going to be my, let's call it my pink problem over here. Now, I'm going to change the pink problem just a little bit. Instead of having theta in this spot, which is kind of similar to what we saw in the blue problem, I'm going to actually move theta to sit up here. Now, looking at this, wherever the angle that you have is, we never use the right angle, wherever that angle is dictates what side is your opposite and which side is your adjacent. Fortunately for us, the hypotenuse will always be the side that is across from the right angle. So this will be our hypotenuse over here. Now, across from theta is going to be your opposite side, and next to theta is going to be your adjacent side. So let me actually get rid of that theta altogether with white. All right. So, in this situation, if theta was in that different location, then for the sine will still be the opposite over the hypotenuse, right? Sine, opposite over hypotenuse. So it would be b over c. So for the pink problem, it would be b over c. Cosine would still be the adjacent over the hypotenuse. So in this case, it would be a over c. And tangent would still be the opposite over the adjacent. So this would be b over a. Now, again, cosecant, secant, and tangent are just flips of these. So this would be c over b, c over a, and a over b. However you choose to remember it, that's up to you, but what's important is that you got to be able to produce those values accurately every time. Now let's get to an actual problem. So in this situation, we are being asked to find the exact values of the trigonometric functions of theta. So what that means is we're being asked to find sine, cosine, tangent, cosecant, secant, and cotangent. Now, again, SOHCAHTOA is our best friend here, because that helps us remember those relationships. So in this situation, theta is this angle, which means the side opposite of that, or the side across from that, will be your opposite. Obviously, the side across from the right angle is your hypotenuse, and the side that's remaining is your adjacent side. The best thing you can do in every problem is, given an angle theta, first start by labeling what is the opposite and the adjacent and the hypotenuse. So in this situation, sine is the opposite over the adjacent, so it would be 8 over 17. Cosine is the adjacent over the hypotenuse, so this would be 15 over 17. And tangent is the opposite over the adjacent, so it would be 8 over 15. Now, cosecant, secant, and cotangent are just flips of those. So cosecant is 17 over 8, secant is 17 over 15, and tangent is 15 over 8, or cotangent is. And we're done, right? We found the exact values. Now, what we're really doing when we do this right triangle trig is we are finding the relationship between the side lengths of a right triangle and a given angle in a right triangle. This is a relationship between the two. It's how they're connected. Let's look at our second problem here. Now again, SOHCAHTOA is how I remember these initial three relationships. So theta that we are given is in this side, which makes 2, the side across from it, the opposite side. The side across from the right angle is still going to be the hypotenuse, always is, always will be. And then whatever's left is your adjacent side. Now, in this situation, when we get to sine, sine will be 2, right? Or it's the opposite over the hypotenuse, so it'll be 2 over 2 square roots of 5. Now, this can actually be simplified and reduced. We can reduce the 2 over 2 into 1 over 1 square root of 5. And of course, this 1 doesn't necessarily need to be there. So we would say sine of theta is equal to 1 over the square root of 5. Now, when we look at the cosine, cosine is the adjacent side divided by the hypotenuse. So the adjacent side is 4, and the hypotenuse is 2 square roots of 5. And again, we have some simplifying we can do here. So looking at this, 2 goes into 4 2 times, 2 goes into 2 1 time. So I'm going to be able to write this as 2 over 1 square root of 5. And again, the 1 doesn't need to stick around. If it is, you're not wrong. If it isn't, you're not wrong either. Then finally, we get to tangent. Tangent is, of course, going to be the opposite over the adjacent. So that will be 2 over 4, which can then reduce down to be 4 over 2. Or I'm sorry, not 4 over 2. I'm jumping ahead. 1/2 when I reduce those. Now, the nice thing about this is since we've already done the reduction, we shouldn't have to think too much more about it. Actually, I lied. So we are going to want you to go a little bit further now that I think about it. We also, in this situation, yes, we reduce the 2 over 2, but we also want to rationalize the denominator here. So if you think all the way back to when we were doing that pre-work, to rationalize the denominator, I would multiply by the square root of 5 over the square root of 5, and this would give me the square root of 5 over 5, because square root of 5 times square root of 5 would give us the square root of 25, and the square root of 25 is just 5. So this would be my final answer for that. Looking at the other one, if I wanted to rationalize this, I would multiply it by the square root of 5 over the square root of 5. So this would give me 2 square roots of 5. And essentially, when you multiply a radical by itself, the radical disappears and you're just left with whatever was inside. So this would be our rationalized denominator there. Now, as we move forward through this, one thing we should realize is that essentially 1 over the square root of 5, what we started with here, is exactly equal to this. If we punched in these values, we would get the same thing. Same with this expression being equal to this one. And you can verify that relatively quickly on a calculator by just punching in second square root of 5 divided by 5. And then punching in 1 divided by second square root of 5. And we find out they are exactly equal. So when I think about cosecant, secant, and tangent, I do realize they're just flips, but let's flip the one that makes sense. If I were to flip, so let me color code these here. So this is the same thing as this. And this is the same thing as this. Now, we are not allowed to give our final answer with a square root in the bottom. So think about it. If I were to use the second expression here and I flipped it, 5 over the square root of 5, then I'm going to have to rationalize that again. But if you go back to before you rationalized and you flipped this one, that would have given you the square root of 5 over 1, which is just equal to the square root of 5. So there's no flipping that would need to happen or no rationalizing. Same thing with this one. So if I take 2 over the square root of 5 and I flip it, that would be the square root of 5 over 2, and I would be done. Now it is important to realize if I would have taken this expression, 2 square root of 5 over 5, and I flip it, then I would get 5 over 2 square roots of 5, and I would have to rationalize. So to rationalize, I would come over there, and I would multiply by the square root of 5 over the square root of 5. 5 times the square root of 5 will be 5 square roots of 5. Square root of 5 times square root of 5 is just 5. 2 times 5 is 10. 5 over 10 reduces down to be 1 square root of 5 over 2, which is what we got already, right? So I'm kind of trying to show you a shortcut, just trying to think which form makes more sense. For this bottom one over here, if I were to just flip this, this becomes 2 over 1, which is, of course, just equal to 2. I think we got one more problem to look at here. So in this situation, it says find the exact value. The exact value means we do not want decimals here. If you give me a decimal, even if you give me 8 decimal places, you don't get the right answer, or you're not going to get marked correct for that. In this situation, we want to find the exact value of each of the trig functions. So now instead of saying theta, since we are being given an angle, that's going to tell us which one they want us to go off of. So in this first problem, they say find the sine of 60. Well, that means go to your 60-degree angle. Obviously, your hypotenuse is right over here. Based off of that 60-degree angle, this would be your opposite, and this would be your adjacent. It's always based off of the angle you are working with. So our sine of 60 degrees would be the opposite, which is the square root of 3, over the hypotenuse, which is 2. Since we don't have a square root on the bottom, we are done at this point. Now, in each of these other problems, notice how our angle switches. Now we're going to be talking about the 30-degree angle. And when we talk about the 30-degree angle, what that means for us is that our opposite side and our adjacent side are no longer that. Because if I'm talking about the 30-degree angle, then the opposite of that would be 1, which would make the adjacent side the square root of 3. The hypotenuse, you may notice, did not move in this situation. So using those new ones, now when I look at the sine of 30, the sine of 30 would be equal to 1, right? It's the opposite over the hypotenuse, over 2, 1/2, which again shows up right here. Now for the cosine of our 30-degree angle, it would be the adjacent, which is the square root of 3, over the hypotenuse, which is 2. Now we're not going to dive into this right now, but it is worth noting there's an interesting relationship here. The sine of a 60-degree angle is the same as the cosine of a 30-degree angle. We'll talk more about that later, but for right now, it's just interesting to know. And then as we get to the tangent of 30, that would be the opposite over the adjacent, so it would be 1 over the square root of 3. And then we would rationalize that, so we'd multiply by the square root of 3 over the square root of 3, so this would be the square root of 3 over 3. Now for each of the other 3, they are just flips. Sine goes with cosecant, so this would be 2 over 1, which is equal to 2. Cosine goes with secant, so this would be 2 over the square root of 3. Now we do need to rationalize that, so we'll multiply by the square root of 3 over the square root of 3, which will make this 2 square roots of 3 over 3. Because the square root of 3 would be the square root of 9. Square root of 9 is 3. Last but not least, the cotangent of 30. We could come over there if we were to flip this guy, 3 over the square root of 3. We would need to rationalize, so we'll multiply by square root of 3 over the square root of 3, which would be equal to 3 square roots of 3 over 3. And then, of course, your 3's cancel out, and you'd just be left with the square root of 3. Now, again, if you did realize a shortcut there, if you would have taken your initial before you rationalized and just flipped that, you would have gotten to the same answer a little bit quicker. That is your basic review of your 6 trig functions. If you have any questions, please don't hesitate to reach out to me, ladies and gentlemen. Thank you very much for watching the full video. Have a good day.